Hello everyone, I am Ishan Dave from University of Central Florida, and here I am presenting our AAAI 24 work, No More Shortcuts, Realizing the Potential of Temporal Self-Supervision. This work is done with Simon Jenny from Adobe and Dr. Mubarak Shah from University of Central Florida. So first I'll provide a quick review of our major contribution. We are proposing a self-supervised video representation learning method. We first identify and remove the local patch-based shortcuts in the temporal pretext task. And we also propose a more challenging frame level pretext task compared to the traditional clip level pretext tasks. Our method is suitable for various downstream applications, for example, high-level semantic recognition tasks such as video-to-video retrieval, action recognition, multi-level video classification. So which is like from a video, one needs to identify various entities, for example, action, objects, scenes, etc. And it's also suitable for low-level temporal correspondent tasks, for example, video object segmentation and post-propagation. Going into the details, we'll first talk about motivation, which is like why do we need video self-supervised learning. Then we'll talk more about like role of temporal pretext task in self-supervised learning and how we identify and remove the temporal pretext task shortcuts. Then we'll describe our framework, some experiments, and conclusion, and with some future work. A key motivation for video self-supervised learning is that video models are more data hungry and annotating videos are more costly compared to annotating images. And so a solution would be learning from unlabeled videos, for example, videos which are available on the internet. A temporal pretext task, it's a very effective way of learning spatiotemporal features in a self-supervised way. So some example of temporal pretext task includes frame order verification task. For example, if the sequence contains in order frame or out of order frames. Or it could be a playback speed prediction where a video is played at multiple playback rates and the task is to classify the speed of the video. To understand the shortcuts in temporal pretext tasks, let's look into the pre-processing of input clip from the original sequence. So from an original sequence, regularly a fixed region is selected and it is cropped throughout the whole sequence. So it means all crops would cover the same region. So it is called frame consistent cropping. So here we are considering a pretext task where a model needs to identify which frame is out of order or not. So from the original pre-processed sequence, we randomly replace a frame there, for example, a red highlighted frame here. And so model is asked to solve which frame is out of order. And by solving this task, we expect model to learn like useful spatiotemporal features, for example, how entire actor moves throughout the sequence. Let's look into the input frame, which is pre-processed through the frame consistent cropping. So if we look at the small region here shown in this yellow ring, we see a sudden change in the out of order frame. So which counterfeits our original goal of learning the how entire object moves through the sequence to solve the task. We can just solve the task by looking into the small observation. So we can say that like this kind of small local patch shortcuts exist and it hinders the learning of useful spatiotemporal features. To resolve the issue of local pet shortcut in temporal pretext task, we propose using frame-wise cropping, which is like independently cropping each frame from the original sequence without maintaining the temporal consistency. So now if we look into the small patches here, we don't see any similarity regardless if the frames are in order or out of order. So to solve this kind of pretext task for which frame is out of order, a model really needs to look into the how entire actor moves throughout the video, and it model ends up learning really good high level temporal correspondence of the features. Prior temporal pretext tasks were designed to make a sequence level or crypt level prediction, which is in a way too simple for recent video models, and it doesn't end up learning effective spatiotemporal features. So we propose more challenging frame level pretext tasks, for example, out of order frame localization. So compared to the prior frame order prediction, which was just doing binary classification if the whole sequence contains in order frames or out of order frames, we look into the more dense task of localizing it, like which frame is out of order. So for in this example, with the fixed skip rate of 4, from 24 to 60, this frame is out of order. So that's why it has a self-supervised target 1 and rest of them are zeros. And similarly, we have a time-varying skip rate prediction pretext task as well. So compared to the prior pretext task of varying the whole sequence with a single skip rate, we vary each frame with a fixed set of skip rates. And task is to predict skip rate between each consecutive frames. Let's put all components together. Starting from the input frame sequence, we pass each frame to the image encoder, which is pre-trained with the image self-supervised method, for example, Dino, and adding the position embedding and passing it through the temporal self-attention layer, we get output tokens for the each frame for the input sequence. And we classify each output token if it is in order or not for the out-of-order frame localization pretext task. And we take the difference of the consecutive tokens and classify them into the skip rate classes. So after pre-training our method in self-supervised way from a large-scale dataset kinetics 400, we evaluate it for action-related downstream tasks. We consider comparing with various prior works, for example, prior work which includes temporal pretext tasks, contrastive learning-based methods, and also recent mask image modeling-based methods. And we evaluated for three protocols: action linear classification, which is training a single layer on top of the frozen features; action full fine-tuning; and video-to-video retrieval from frozen features. And we consider various data sets, for example, UCF1 on HMDB in Kinetics 400, which are collected from web. Something V2, it's basically a human hand and object interaction data set, and it requires a really good temporal understanding. Then NTU60, which is a indoor data set, and Shareds is a multi-label action data set. So we see that on all of the data sets, our method consistently outperform all prior works. And in the action fine-tuning, it gets the competitive performance. And on video-to-video retrieval, it outperforms by a good margin. So our method is state-of-the-art in video-to-video retrieval and linear classification. So apart from actions, we also look into the other aspects of semantics and videos. For example, actions, concepts, scenes, or objects in a multi-level setting in video. So we consider a very large-scale data set, holistic video understanding data set, which is in the scale of kinetics. And we consider a linear evaluation protocol. And we comparing with the most recent prior work, we see that our model, it outperforms in all entities and also gets a higher overall score. We also evaluate our model on low-level temporal correspondence tasks, for example, video object segmentation. So here goal is to propagate the mask of the first frame without performing any fine-tuning. So here's our qualitative results. And we follow the protocol of Davis 2017 dataset, and we outperform all other video self-supervised works across the metrics. Another correspondence task we are solving here is video pose propagation. So here key points of the pose are given for the first frame and we need to propagate through the sequence without performing any fine-tuning. So here are some qualitative results and comparison with the prior work. So apart from various downstream tasks, we are also performing robustness analysis for the input perturbation. So input perturbation may look like this, where each frame may be perturbed with motion blur, Gaussian blur, or various kind of speckle kind of noise. So we are considering a video retrieval task and see that our method, it's more robust to this kind of input perturbations. So this signifies our method's importance in the video search applications where we need to find duplicate content over the web. So let's understand the individual contribution of each component in our framework, starting with the initialization baseline, which is a image self-supervised learning baseline. When we add the frame-wise augmentation with the contrastive learning framework, we see a small boost there. However, adding the individual pretext temporal task, we see a significant boost in the result across the all protocols. And finally, adding all components of both temporal pretext task and frame-wise augmentation, we get our best result. So here we are comparing traditional clip level temporal pretext tasks to our proposed frame level temporal pretext task. So for the sequence order verification task, while going from clip level to the frame order verification task, we see that we get 4 to 9% boost across the protocols. And this is also true for the skip rate prediction. So we see that while just going from frame clip level to the frame level, it contributes significantly to our improvement. In summary, we have proposed video self-supervised learning method on top of the image self-supervised method by breaking shortcuts in temporal pretext tasks and by proposing more challenging frame-level temporal pretext tasks. Our method is suitable for high-level downstream tasks, for example, action recognition, video-to-video retrieval, and multi-level video classification. And it's also suitable for temporal correspondence tasks, for example, video object segmentation, post tracking, and gate recognition. And key attraction to our method is that it doesn't require full fine-tuning, and it gets absolute state-of-the-art for video-to-video retrieval and linear video classification, which is most desirable in video search applications. Thank you for listening, and for more information about our project, please contact on my email ID, and for qualitative results, look into our project webpage.